A linear equation in two variables is an algebraic expression containing only two variables and an equality sign. In this chapter, we will learn various methods to solve a pair of linear equations in two variables known as the system of linear equations. In this chapter, we will study the following concepts: the graphical method and the algebraic method. Pair of simultaneous linear equations in two variables. An equation in the form ax plus by plus c is equal to 0, where a is not equal to 0, b is not equal to 0, and a, b, c are real numbers, is called a linear equation in two variables. Two linear equations in two variables taken together will form a system of simultaneous linear equations in two variables. In general form, pair of linear equations in two variables is a1x plus b1y plus c1 is equal to 0. a2x plus b2y plus c2 is equal to 0, where a1 square plus b1 square is not equal to 0 and a2 square plus b2 square is not equal to 0. For example, 2x plus 2y plus 7 is equal to 0. Graphical method. When we draw the graph of pair of linear equations in two variables, then there are three possibilities that exist. First is intersecting lines. The two lines will intersect at a point. Then there exists only one point common to both lines. Hence, coordinates of this point gives unique solution. Second is parallel lines. The two lines will not intersect, that is, they are parallel. Hence, there is no solution. Third is coincident or overlapping lines. The two lines will coincide or overlap. Then, every point on one line is also a point on another line. Hence, there are infinitely many solutions. Consistent system. A system of pair of linear equations in two variables is said to be consistent if it has at least one solution. Inconsistent system. A system of pair of linear equations in two variables is said to be inconsistent if it has no solution. Here is a table which shows the nature of system of pair of linear equations in two unknowns. First system of equations is 2x minus 7y plus 42 is equal to 0, 3x minus 3y minus 6 is equal to 0, in which 2 by 3 is the value of a1 by a2, minus 7 by minus 3 is the value of b1 by b2, 42 by minus 6 or minus 7 is the value of c1 by c2. After comparing these ratios, we found that a1 by a2 is not equal to b1 by b2, so these lines are intersecting and we get exactly one solution. Hence, system is consistent. Second pair of equations is 3x plus 6y minus 90 is equal to 0, 2x plus 4y plus 40 is equal to 0, in which 3 by 2 is the value of a1 by a2, 6 by 4 or 3 by 2 is the value of b1 by b2, and minus 90 by 40 or minus 9 by 4 is the value of c1 by c2. After comparing these ratios, we found that a1 by a2 is equal to b1 by b2 is not equal to c1 by c2. So these lines are parallel lines and we get no solution. Hence, system is inconsistent. Third pair of equation is x plus 4y minus 30 is equal to 0, 2x plus 8y minus 60 is equal to 0, in which 1 by 2 is the value of a1 by a2, 4 by 8 or 1 by 2 is the value of b1 by b2, minus 30 by minus 60 or 1 by 2 is the value of c1 by c2. After comparing the ratios, we found that a1 by a2 is equal to b1 by b2 is equal to c1 by c2. So, these lines are coincident lines and we get infinitely many solutions, and hence system is dependent or consistent. Solve the following system of equations graphically. 3x minus 5y is equal to minus 1. 2x minus y is equal to minus 3. Solution. Given equation is 3x minus 5y is equal to minus 1. This implies y is equal to 3x plus 1 divided by 5. Tables of values. When x is equal to minus 2, then y is equal to minus 1. X is equal to 3, then y is equal to 2. X is equal to 8, then y is equal to 5. Also, 2x minus y is equal to minus 3. This implies y is equal to 2x plus 3. Tables of values. When x is equal to minus 2, then y is equal to minus 1. X is equal to minus 1, then y is equal to 1. X is equal to 0, then y is equal to 3. The two lines intersect at the point minus 2 minus 1, hence x is equal to minus 2 and y is equal to minus 1. Is the only solution of the given system of equations.
Graphical representation of a system of linear equation. We are working on this system of linear equation. 2x plus 3y minus 30 equals 0 and 4x plus 6y minus 72 equals 0. We rewrite equation 1 as y equals 30 minus 2x by 3. This helps us to tabulate the value of y corresponding to values of x. We draw the xy axis on a graph and plot these points on it, and with ruler draw a line passing through them. Now consider the second equation, 4x plus 6y minus 72 equals 0. That is same as y equals 72 minus 4x by 6. This gives us the value of x and y satisfying this equation. Now we plot them on our graph paper and using ruler draw a line passing through them. Note that the line is parallel to the first line. To understand how this happens, note that if we divide the second equation by 2, we get this. So, if the first equation is px and second is qx, then qx is px minus 6. So, the solutions of px and qx always have a constant difference. And this is why there is a constant distance between the two lines. Area of region bounded by lines and axes. In this problem, we have this system of two linear equations. The first equation is satisfied by the following values. We plot them on the graph, draw a line passing through them. Similarly, the second equation is satisfied for these values. Again, we plot them on graph paper and we draw a line through them. Note that the lines have formed two triangles, one along each axis. The height of triangle PQR, that is the distance PM between the point P and the x-axis, is 3 units. And its base length QR is 10 units. So the area of the triangle PQR is half of 10 times 3, that is 15 square units. Now consider triangle SPN. The height is again 3 units and the base length SN is 10 units. So, the area of triangle SPN is again 15 square units. So, the ratio of the area of the two triangles is 15 is to 15, that is 1 is to 1. Area of region bounded by lines and axes. We are working on this system of three equations. We plot them on the xy axis. The equation x equals 3 gives a constant value to variable x, so that y can take any value. So this line represents the given equation. Similarly, x equals 5 fixes the value at 5 units to the right of y-axis. Now, these are some points satisfying the third equation. So we plot these on the graph and draw a line passing through them. Therefore, this is our required bounded region. Clearly, this is a trapezium. We know that area of trapezium is half of the sum of parallel lines times distance between them. That is, half of BC plus AD times CD. The length of AD and BC are known to us. CD is OC minus OD, that is 2 units. On substituting the values in the formula, we get the area of the required quadrilateral or trapezium is 8 square units.